Okay, so I wanted to finish up with the 4 components of a true experiment. We hit the first 3, but I didn't talk about the last one. Who can tell me what the first 3 components are of a true experiment? Random assignment, that's one. So we have people that we want to learn something about, so we randomly assign them into different groups. If we want to do a study on a drug to see if some drug helps to cure cancer, we get a group of people with cancer and we randomly assign them. Some get the drug and some don't get the drug. And we want to see if those who got the drug end up doing better than those without, more than we would have expected due to chance. Right? So random assignment. What else? Random selection, which means that we take from the population of people that we're interested in. So in the ideal true experiment, we would randomly select from all people who have cancer. Right? We don't want the people who don't have cancer because we're interested in learning, but all the people in the population of interest. What was the next one? Control. Okay, and what's the deal with control?
Control all sides.
Yeah, we want to control for other things that might influence the outcome, the dependent variable. So maybe the time of day that people get a shot might have some effect on the cure of cancer. Maybe if they get it early in the day before they do their stuff, maybe that's important. So you want to have everyone take the drug at the same time. Does that make sense? There are lots of things that you can control. And the types of experiments that I do, I have people sit in front of a computer and press buttons. I don't want them to get distracted by outside things, so I like to turn down the lights and make sure that no one else is in the room with them, so that way they can focus on the task. That's a control. I'm controlling for the other things that might affect what they want, and by doing that, I'm trying to eliminate any confounding variables. The extraneous variables are still working, but I'm making them all constant. Right? One of the questions from the study guide is, what is a constant variable, or something like that. A constant is something really that's not a variable. It's something that stays the same. Right? So her sex is female. That's going to stay the same. That's constant. If you look at the whole room of people, we can consider sex as a variable, right? Male, female, male, female. It's varying over people. But for one person, that thing is staying the same. All right, so we've got random selection, random assignment, control, and then finally, manipulation. What's the deal with manipulation? We're changing something. So in that drug study that I mentioned, we're going to give one of the groups of people the drug, and we're not going to give the other groups of people the drug. Does that make sense? We're manipulating something. This is something that we have control over, in the sense that we can change it. Some things I really can't change. I can't change your sex. I can't make her male, right? Even if I can change her physical appearance, I could send her to a clinic and they could do some surgeries that might change her, but still her genes, her chromosomes, she'd still be a female, right? So I can't change that. Now, if we're doing this drug study, and I give one group the drug and I don't give the other group a drug, there might be a problem. What might be a problem if I gave, let's say, all the people in the drug group get a shot and the other people don't get any shots? So you guys all have cancer. One group, I'm going to give them shots. The other group, I don't give you anything. There's a problem with that. There's a confound. What is it? If I give them a shot and they know they're in a study that's supposed to be looking at whether this drug treats cancer, what might they think? What do you think? You have cancer. Do you want to die from it? You got a shot. What are you thinking? Inshallah, you know, this will cure cancer and I'll be okay, right? But this group, I didn't give him anything. I just said, well, thanks, see you guys later. So what are they thinking? They think, oh crap, I didn't get anything, I'm going to die, right? So this group is more positive than this group. Does that make sense? There's a confound there. So maybe the people that are more positive will end up living longer. They'll have a better chance at fighting cancer than those who are negative. And this is actually something that works. So the outcome of cancer is somewhat dependent on people's mood. So I've confounded mood with the treatment. So how can I control? How can I use control to eliminate this confound? Before I gave him a shot, and I didn't give her anything.
Tell this group that you're doing pill, but you're not doing it.
Yeah, so I could give the other group a fake pill or a fake shot, right? I could give them a shot, which just like saline solution, right? Where it doesn't actually do anything. But that way, I'm giving them both shots. So they both think, oh, I got a shot, hopefully I'll get better. Does that make sense? So by doing this, we have eliminated a confounding variable by exerting control. The manipulation was to actually give you the drug and not give you guys things. But the way we're giving both groups shots, we've controlled. All right, so differences between experiments and the correlational studies. We can look at random selection. We talked about having random selection in experiments. Do we have random selection in correlational studies? Can we have random selection in correlational studies?
No, they have to be related.
It says you have to be related somehow, but I don't know if I buy that. So maybe I'm not going to do an experiment. So what's something that I can't manipulate? Sex, right? So I want to see if there's a difference between males and females and how many Facebook friends they have. Okay? So I'm not going to manipulate anything. Can't manipulate your sex. And so this is a non-experimental technique, but I can randomly select the men and women that I use, right? I can randomly select from the students at Shahir, or from all the students in the Turkish universities, or from all the students in the world, right? So yes, in correlational studies, I can use random selection. In experiments, you have to do random assignment. You're going to flip a coin, you're getting the drug, you're not. You're not, you are, you're not, you're, right? So I'm randomly assigning. How about in correlational studies? No. Why not? Why can't I do this random assignment? Because I can't do something else. I want to look at men and women and Facebook friends, right? Can I assign him to be a man? I can't assign him, right? Because I can't manipulate. So with correlational studies, we don't have random assignment. It's something that we can't later manipulate. Control, we have controls in experiments. Can we have controls in correlational studies? So I turn the lights down. Can I have people take surveys, have men and women come into my office and turn the lights down and make sure that no one else is in the room with them? Yes! Yeah, so I can use controls in both of these things. Finally, in experiments, you have to have a manipulation. If you're not manipulating something, it's not an experiment. With correlational studies, you don't have a manipulation. Can't manipulate sex. I can't manipulate abuse. Remember how I talked about we could do this study with children, and I could randomly select orphans, and I could randomly assign them to the abused group and the unabused group, right? And I could abuse them. But I said that this isn't ethical. We shouldn't do this, right? So if I'm not going to do that, if I'm not manipulating abuse, all I'm doing is measuring it. If I'm just measuring it, I'm not manipulating it, it would be a correlational study. So most of the studies where people are looking at things like abuse, they're not manipulating abuse, they're not hitting kids. They're looking at kids who have been hit and kids who haven't been hit, right? And since they didn't manipulate it, it's a correlational study. So why don't we always do experiments?
Because there is some ethical issues.
There could be some ethical issues. I think it would be unethical to take a group of kids and just say, okay, I'm going to beat you guys, and I'm not going to beat you guys, right? I mean, think about when we were talking about the purposes of science, and one of the last purposes of science and psychology was to improve things, right? So by learning about abuse and criminality, we can improve things, but if I'm actually abusing the kids to get that knowledge, I'm making things worse for those kids, right? So it's unethical. So another reason that we might not use an experiment is because we can't manipulate something. I can't assign, like, let's say I want to do a study about başarılı versus başarısız and how they do on math tests, okay? I can't, like, say, okay, you're going to be in the başarısız group, right? to say that you can be in the Boucher-Lou group, right? Because if she doesn't have a problem with, not wearing a headscarf, covering up, that's no big deal. But for those of you who believe you have a religious obligation to wear this, taking this off is a problem, right? So I can't manipulate that. I can measure it. I can get a bunch of females and look and see if they have a headscarf or not and how they perform on a math test. But I shouldn't be manipulating something like that. All right. So let's talk about stats and graphs and fun stuff. Okay, so an important part about psychology in all of the sciences is showing relationships between things, right? We want to see if there's a link between abuse and criminality. We want to see if there's a link between therapy and getting over depression. We want to see if there's a link between age and the types of tasks that people can do, right? We're interested in relationships. Now, the graphs usually are showing relationships between two or more things, right? So here we've got 3 different types of graphs. What's this? Line. Bar graph. Scatter plot, exactly. Now, not all graphs and charts show relationships. So some of you guys may have seen a pie chart, right? And the pie chart just shows what percent of the whole a certain thing is comprised of. So we can make a pie chart here for women versus men in this class, right? It's not showing a relationship between anything. It's just showing how many men and women we would have. Okay, labeling. If we have a graph and we wanted to communicate information easily, what types of labels do we need? So we need to label the independent and the dependent variables, right? So typically, which goes where? What goes up here? Typically, the dependent variable is on the x-axis. And what's on the y-axis? The independent variable. If we can identify the important variables, then we have some idea about what we're looking at, right? If you don't give these labels, you have no idea what you're looking at. But now, you see, okay, we're looking at the number of Facebook friends as a function of sex, right? So here we have some idea that one sex has more friends than the other. What else do we need to make more sense of this? We need units, right? Is it males that have more friends or females that have more friends? Maybe I'm making this assumption that more is this way, but it could actually be the other way. So if I label the units, we have a better idea of what's going on. Okay, so females and males going from 0 to 500. So we see that on average, females have about 440 friends and males have about 270 friends. I made these data up. These are just, don't pay attention to this. Didn't do a study to do this. Did do a brain thing to show you guys an example of a graph. Okay, the independent variable is often called a factor. This is going to be important when we define what an interaction is later. A factor is something that is that the dependent variable is supposed to rely on. And here we have levels of the factor. So we have female and male. So sex, we have 2 levels. We could talk about a different factor, grade, in terms of like 1st, 2nd, 3rd, 4th, senior year in college, right? So how many factors, or how many levels does that factor have? It has 4. If we included the prep, we would have 5, right? Okay, and finally, if we put up a descriptive title, we can sort of summarize the main things that's going on in the graph. Females have more Facebook friends. Great. Cool? Is there anything I'm missing? All right, so hopefully the previous graphs that I showed you should make more sense now. Again, I'm just making these numbers up to demonstrate how graphs communicate information. So imagine that we're looking at how number of kids affects the free time that people have. So what is this saying? As you have more kids, what happens?
Less free time.
Yeah, as you have more kids, you have less free time. The number of kids is the independent variable. Free time is the dependent variable. What extraneous variables might there be? for this. What other things affect free time?
Work.
How much work you have to do, right? So that's an extraneous variable. When would that extraneous variable be confounded? Might we expect that work is associated with number of kids?
No, tutoring. If you tutor your kids.
If you're tutoring kids, then you have more kids?
No. Okay, if you have 4 kids to tutor,
Uh-huh.
to teach them at home, then you have less time, free time.
Oh, I see. So the reason that you have this is because you're actually doing more tutoring, right? So the number of kids that you have is sort of confounded with the amount of time that you spend on the kids. It could be in tutoring, it could be in other things too, playing with them, right? Imagine that you have more kids, so you need more money, right? So you have to work more jobs. If this is actually the case, then we would have a confound. All right, how about this? GPA, the grade point average, as a function of hours that people spend a day. So what can we say about this?
Because there are some people that will study for a longer time and they will have low GPA.
So the people that study for a longer time have a low GPA?
It's possible.
It is possible that someone could study for a long time and has a really low GPA, right? Now, you see there's variability. So some people here, they don't study very much at all, but they have a really good GPA, and someone else who studies the same amount of time has a really low GPA, right? So there's some variability. But on average, what's happening? As the number of hours studying goes up, the GPA goes up, generally speaking. Okay, so let's look at 3 common statistics that can help us make more sense of the information that we see in graphs. So the mean, what is the mean? The mean is the average, or what people often commonly refer to as the average. They want to give me anything else?
Like something that is common.
Something that's common. It's interesting because the mean actually doesn't ever have to be present, depending on what values you look at it. Imagine that there's something and it's either male or female, and you want to see if there are more males or females at Shahir than at some other university. Now, the mean is like a proportion of males and females, right? It's not actually being a female or not. But what does it tell us? In physics, what does the mean tell us?
It's not the middle value, is it?
It's not necessarily the middle value. Sometimes it is, sometimes not.
Central tendency.
Yeah, it's the measure of central tendency. It's the balance point, right? If you have a teeter-totter, if I want to play teeter-totter with my daughter weighs like, I don't know, 12 kilos, and I weigh 100 kilos. So she sits on the end of the teeter-totter, and where do I sit? I sit close to the middle of the teeter-totter, right? That way we create this balance where the mean, that balance point, are one and the same. So it's the average score, the balance point. It's the point all other points on average are closest to. The mathematical formula, the sum of all the scores divided by the number of scores. So if he took my quiz and he got a 5 and she got a 4, what's their mean? 4.5, right? I just take everyone's scores, add them up, and divide by the number of scores that I have. The standard deviation, what is this?
How spread.
It's basically how spread out things are. It's an index of variability. How variable is something in a population? I'm not going to talk about the formula. You can learn about the formula when you take stats, or you can come into my office and we can discuss the formula. But for this class, I want you to know it's how spread out scores are around the mean. Now imagine that we have 2 sets of scores, okay? And we have the exact same mean. So we have scores of 1 and 3, so they took my 5-point test, and he got a 1 and she got a 3. What's the mean? 2. Now imagine a different group of people. He got a 0, he got a 4. What's the mean? 2. The mean is identical in both of these cases, right? In which one are things more spread out? It's more spread out over here, right? Where the scores are farther on average from the mean. So the one with the bigger standard deviation is the second one. All right, so if we look at the different types of graphs, sometimes we can see means and standard deviations. So here we've got a line graph. Where are the means here? The means are visible. We had number of kids, 0, 1, 2, 3, 4, 5. Huh? So the middle right here. So this is the mean for everyone, right? There's some other means too. We have a mean for the people with 0, and we have a mean for the people with 4. Where are those means? Does anyone know? Ejin, can you, this is the laser pointer. Can you point to me where there's a mean on that? Where's the mean for people that have 1 child? Try again. Yes, that's it, yes. So here we have the mean for people that have 0 children, the mean for people that have 1 child, for 2 children, and so on and so forth. Right? So for each of these points, remember we had 0, 1, 2, 3, 4, 5 here? Each of these points represents the mean for that group of people. Right? If we collapse over all the different groups, we have a mean somewhere about there. Right? If we have the same number of people in each of those groups. Okay, so the means are shown for each independent variable level, for each factor level. How about here? What are the means? This is the laser pointer. So where is the mean for the females? Ding, ding, ding. Yes, that's absolutely right. So on the bar graphs, the means are basically the tops of each of those bar graphs. Does that make sense? So women, on average, had however many, like 440 or something, and they had fewer. Right? That's the mean for all the men. That's not one man's score or one woman's score. That's the mean of all the men and the mean of all the women. How about here? Where's the mean? This is the laser pointer there. So where's the mean? No, for the scatter plot. So the mean is right in here. I don't know if that particular point is the mean. Each one of these points represents one observation. So he studies, I forget what the number was, some small amount every week, and he has a really bad GPA. And this person studies a little bit more, and they have a little bit better GPA. And this person studies a little bit more, and they actually have a worse GPA. So each of those individual points shows a score on GPA and the score for the number of hours studied. So if we want to look at the average, GPA, we would figure out how far each of these differs from the mean. So what's the mean sort of in the middle here? We got some point maybe in there somewhere, right? And the mean in terms of the number of hours that are spent, we can get the hours that they spend, add all of the hours that the individuals spend, divide by the number that we have, and again we've got something sort of in the middle. So somewhere in the middle there, we have our means for the GPA and the means for the hours that people are spending. Does that make sense to everybody? Alright, so the mean isn't directly shown, but you can calculate it. You can sort of get a quick idea just by visually inspecting. Whoa. Sometimes when I edit the PowerPoint, things get screwed around, so I'll fix that for the stuff that goes on the web. Okay, there are no standard deviations in the basic line and bar graphs. Right? We have the means, but we don't know how spread out people are. Maybe one person with 0 children, they have tons and tons of free time, and other people have absolutely no free time. Right? And maybe for people with 1 child, they've got, everyone's sort of close to that mean. So we can't actually figure out what the standard deviation is by looking at this. There are some times where in journals, they'll indicate, oh, this is going to be bad. Yeah, that's what I thought. Let's go back. So where you'll see these little like bars, they're called whiskers, and the whiskers help you figure out how far spread out the scores are around the mean. So if you've got a whisker like that, you know that there's less of a standard deviation than if there's a whisker like this. But if they're not in there, you can't calculate it. Now, we can calculate the standard deviations by looking at the scatter plot. We can see how much spread out things are, or how little spread out things are. So let's ask, by looking at a scatter plot, boy, this is really giving the system a heart attack. What has a greater standard deviation? This set of scores or this set of scores? Who can tell me, where's there a greater standard deviation? And the second one, how do you know this? They look identical to me. The numbers are different. That's exactly right. So even though the points are similarly spaced, you can see that here the range goes from 0 to 2, whereas here it goes from 0 to 4. So we have things more spread out in this direction. So the standard deviation for the independent variable is greater in this one. How about the standard deviation for the dependent variable? Which is greater? They're exactly the same. They're both spread out in this direction equally much. Does everyone get that? Okay, so they look the same. If we rescale the axes, it's easier to see. So here we have both of these data sets on the same axis, and we can see that there's a lot less spread on the independent variable here than there is there. Good? Okay. So which of these two has a higher correlation? Talked about mean, standard deviation. Correlation was the third one I want to talk about. Which of those has a higher correlation?
First one.
The first one has a higher correlation? How many people say the first one has a higher correlation? Raise your hands higher. Okay, how many people say the second one has a higher correlation? How many people say they both have the same correlation? Can you tell us why they have the same correlation? He's right.
Oh, that's hard. Actually, correlation, I mean, there's no relationship there. I mean,
What do you mean there's no relationship?
No. I mean,
as you have more of the independent variable, you generally, on average, you go up on the dependent variable. There's a relationship there.
there is no, okay, the data for correlation is not mentioned there. Like, okay, can I say it?
Okay, let's define what a correlation is. So the correct answer was neither. Some students, like, they say, oh, teacher, that was a trick question. You were trying to trick me. And I say, I don't try to trick my students. I want to see if you guys know or not. I'm not trying to trick you. But it might be a tricky question. That last one, that was a tricky question, not a trick question. Okay, so some transformations, they don't affect correlation. Transformation, what's a transformation? Have any of you guys in like high school, like you would take degrees in Celsius and have to convert it to degrees Fahrenheit, or maybe degrees Kelvin? How many of you have done that? Wow, very few. Oh, that's depressing. Okay, for those of you who did this, how did you do it? How do you figure out Fahrenheit from Celsius?
There's a simple formula for
Okay.
all those transformations.
And basically, what do? I don't need to know the exact numbers, but the
I
idea.
don't remember the figures, but you see, let's say C stands for Celsius, let's say, equal to Kelvin divided by 360, let's say. I'm making up the numbers. You put the values there.
Good, so he said that you have Celsius and then you divide it by something to get Kelvin. I don't know if I don't remember. I'm a psychologist, but that's exactly right. He divided something in order to get Kelvin. This division is a transformation. How about Fahrenheit and
Adding up and
so 0 in Celsius is freezing. Does anyone know what freezing is in Fahrenheit? It's 32. 32. So you add something. You add 32, and then you do some division as well. So the transformations that you can do anything that stretches out all the squares by some constant amount. So we can multiply or divide everything by the same amount. We can multiply all of our squares by 2, like I did in that one example, right? We had these squares, and then these squares, I just multiplied the independent variable by 2 for all of them, and it spread things out. It stretched it. So anything that stretches or shrinks the scores by the same amount doesn't affect the correlation. And similarly, anything that shifts the scores, meaning like we're adding a constant to them or subtracting a constant from them, doesn't affect the correlation. So anything that stretches or shifts the data by a constant amount doesn't affect the correlation. Other things will screw up the correlation. If we take the square root of everything, that will affect our correlation. Why? Because the square root doesn't change everything by the same amount. Right? Square root of 2 affects 2 much less than it does the square root of 100. So these sort of linear transformations are the things that we can do without affecting the correlation. This is great news for international psychologists, because when we come up with a correlation that's using 1 unit of measurement, like so in America we're looking at temperature and happiness. Do people get warmer as the temperature gets, or do people get happier as the temperature goes up? It doesn't matter if I do that in Fahrenheit and if someone over here does it in Celsius. We'll come up with, hopefully, the same correlations if there really is some relationship out there, right? Okay, so the standard deviations measure how spread out the scores are around the mean. The correlations measure how strongly 2 variables are related, how spread out the scores are around some best fitting line. So in those previous examples, you can imagine a line that you would draw through all those points to describe overall sort of what's happening. Does that make sense? So the line that sort of best describes the average tendency of what happens with the change in the independent variable to how the dependent variable changes is going to give you the correlation. The correlations also measure the direction of the relationship between 2 variables. So the correlation coefficient ranges from 1 to -1. What does it mean if we have a correlation of 1? We have a perfect correlation. How about a -1? Is this an imperfect correlation? It's also a perfect correlation. So a correlation of 1 and -1 are perfect correlations, meaning that there's a very, very strong correlation. So the absolute value is going to indicate the strength of a relationship. If we have a correlation coefficient of 0, what does that mean? There's no relationship at all between the 2 things. What is stronger, or a correlation of 20 or a correlation of -20? They're both the same. How about a correlation of 20 versus -30? Or -0.3, I should say. 0.2 or -0.3.
0.3 is stronger.
Yeah, the -0.3 would be stronger, right? The sign is going to tell you what direction the relationship is going in. Right? So the absolute value of R is going to tell you how strong things are. The closer it is to 1, the stronger it is. The closer the absolute value is to 1, the stronger it is. The closer it is to 0, the weaker it is. The sign tells us the direction of the relationship. So here I have some examples of scatter plots. I don't know what the data are from, but you can see that some of these, they have like data sort of all spread around, and here the data are very close to some line, and here actually they're all falling on a line, right? So here, what type of correlation do we have? It's a perfect positive correlation. What does it mean for a correlation to be positive? As 1 increases, the other one increases too, right? So here, if you look at these 3 and these 2, here, these are all increasing, right? So here we have positive correlations. Here, as 1 goes up, the other one goes down, right? So the higher we are on the dependent variable, the lower we are on the independent variable. So if both things go up, you have a positive relationship, positive correlation. If one goes up and the other goes down, you have a negative correlation. All right, so the absolute value indicates the strength of a relationship. Look at the difference between these and these. Here, basically the directions of the relationships are the same, but what's happening is that some of them you have a lot of spread out along the line that would best describe it. In others you have no spread, right? So here you have no spread around the line. It's a perfect correlation. It's 1. If we had the one over here like that, that would be a negative 1. Here things are getting a bit more spread out, right? So we see a weak correlation. Here things are even more spread out around the line. A weaker correlation here. We have an opposite direction correlation that's equal in strength there. And here we have, it doesn't look like we can put a line in there that best describes it, right? So we have no correlation. Yes?
Okay, point 8, you said it's weak.
Yes. Well, it's weaker than 1. Point 8 is still a very strong correlation.
Okay, now we have point 5. How do we know if it's close to 0 or actually it's close to 1?
So in statistics you learn about different strengths of correlations. So if I asked you something on the test, and I have answers like a perfect positive, a positive, no correlation, negative, perfect negative, I'll be looking at things like that where I'm not actually measuring fine distinctions between is this strong or is this weak. Does that make sense? So typically in statistics something like 0.8 is going to be a very strong relationship. Something like 0.2, which isn't here, is a fairly weak relationship, which actually still might be statistically significant. Right? Okay, it's not the slope of the line that determines R. Notice that each of these, they have different slopes. One's going like this, one's going like this, another one's going like this, right? The slope isn't determining the strength of R. We could, like here, we could make this one go up that way a little bit, you know, shift the whole thing. But what we're doing there is we're applying one of these transformations where we're just adding something to each of the lines or stretching it, right? If we multiply these numbers each by 2, we're going to get something that looks more like that if we put it on a similar scale. Yeah?
What does the slope mean in statistical sense?
The slope is kind of meaningless in the terms of a correlation. What we're talking about is how strong a relationship is between something else. So, like, imagine that we're going to get paid to do something. We're going to clean around shit here. We're going to pick up the choke that's on the ground, right? And I'm going to get paid 40 liras an hour because I'm a PhD. And you're going to get paid like 8 liras an hour. Does that make sense? So, if I work 2 hours, how much do I make? 80 liras, right? There's a perfect correlation. The more hours I work, a perfect positive correlation. The more hours I work, the more money I make. And I can calculate exactly how much money I make if I know how many hours I work. The same can be said for him. If I know that he worked 2 hours, I know exactly how much money he made. He made 16 liras, right? So the correlation is measuring how good we can predict the dependent variable if we know what the independent variable is. Might help to think of things like that, right? So it doesn't really matter if we're going up a lot for each change in the independent variable or a little bit, right? That's why these things are the same strength and correlation even though the actual slope is different. Okay, the more spread out the data are, the weaker the relationship is. The spread doesn't matter if there's no relationship. So examples of correlations. So imagine education and kids. As people become more educated, what happens to the number of kids that they have? Yeah, the more educated people get, the fewer kids that they have. Is this a positive or a negative correlation? It's a negative relation. The more education, the fewer kids. Is it perfect or imperfect?
We have to see the data.
You have to see the data. Yes. If I know that you've had 4 years of, college education, do I know how many kids you have? No. If it was perfect, would I? Yes. If there was a perfect relationship, I would. So this, although it's a positive relationship, I don't know exactly for sure. I can take a guess, but I'm sorry, negative because one is going up and the other is going down, but it's not perfect. The hours we work and the income, if we are getting an hourly wage for the things that we do, we have a perfect positive relationship. If we're getting a salary, so I'm not paid for the hour. I'm paid to teach classes. And it doesn't matter if I spend 1 hour a day teaching classes and prepping for classes, or if I spend 1 hour a day teaching and then 10 hours preparing, right? So there's really no correlation. You have teachers who are working a lot and teachers who are working a little, and their salary doesn't depend on how much they're doing. Ice cream sales and drownings. So as ice cream sales goes up, what happens to the number of drownings? What?
What's a drowning?
Drownings are people like that are swimming, but they don't swim very well, and they die because like fluid gets in their lungs. There's no correlation? There is a correlation. What's the correlation? As people sell more ice cream, what happens to the number of drownings?
It goes up.
The number of drownings also goes up. That's exactly right. It's positive. You guys know this guy? This is Fred Phelps. He's a pastor in America, and he has these signs that say like God hates fads and God hates other things. So maybe he can make a sign that says God hates motto, right? They sell ice cream, and as they're selling more ice cream, people are dying. So we'll talk about ice cream and deaths more next class as we finish up our discussion on correlation. See you on Wednesday. So there was a question about the statistical meaning of a slope, whether there was something meant different by a large slope as opposed to a small slope. And I said that in terms of the correlation, the change in slope is really sort of meaningless. That means it doesn't affect the strength of the correlation. The slope does have some important meanings, but not in terms of the correlation. So with a large slope, what's happening is with 1 unit of change in the independent variable, we have a large change in the dependent variable. With a smaller slope, we have 1 unit of change in the independent variable and a smaller change in the dependent variable. So imagine that we have something with a large slope and something with a short slope. The slope doesn't tell us how good our predictions are. The thing that's going to tell us how well we're able to predict the dependent variable from the independent variable is the strength of the correlation. If the correlation is strong, we'll be just as good at predicting what the dependent variable should be based on some independent variable, regardless of whether the slope is very positive, very negative, or slightly positive or negative. So it's not the magnitude of the slope that's depending the strength of the correlation and vice versa.